former CE NFC, and Director AMD, Dr. D.K. Sinha sir, then additional directors of AMD, and other senior colleagues, many other dignitaries, and my dear friends, a very good afternoon. And of course, we have got a lot of students joined us in our hall. They are from different schools of Hyderabad. And anyway, we have got 2 colleges and 7 schools who have joined us in our hall. And one of the schools, they have joined us through webex. And a lot of dignitaries have joined us online also, many officers of AMD, regional directors of AMD, then INS Mumbai members. And I would like to say a good afternoon to one and all. Dear friends, we are here to listen to a very much awaited talk from a very eminent and accomplished technocrat of our country. So first of all, I will request our beloved Director AMD and Chairman INS Hyderabad branch, Dr. D.K. Sinha, to welcome our chief guest of this function with a flower pot. I request Ms. Shravani to assist Director Sir. Sir, please. Thank you, sirs. Thank you, Shravani. Without any further delay, let me invite Dr. D.K. Sinha, Director AMD, to deliver his welcome address. Sir, please.
Good afternoon. Today's chief guest, Padma Bhushan, Dr. V.K. Saraswat, member NITI Aayog. Rear Admiral Sanjay Chaube Sahab, CMD ECIL. Dr. T. Srinivas, Dr. Sai Baba, N. Sai Baba, former CE NFC. My colleague, Dr. T. Sunil Kumar, Sri Sarvanan, and very senior members of AMD as well as the INS who are joined virtually with us. I would like to take the name of Dr. Mahadevan. He is plus 90 years and he is virtually linked with us. Sri M.V. Verma, Dr. A. Ramarao, N. Rambabu, Mamlan. Many people are there. A.K. Bhatt, Dr. P. Krishnamurthy, Pramod Kumar, Sandeep Hamilton, many senior scientists who are linked with us in this seminar, and my colleagues who are physically present in this hall, and special invitees, the students, college students, school students, and their teachers. So this has become a real, very good lecture hall now with academia, with industry, and with technocrats. With this audience, I am very happy to say that ultimately we have brought Dr. Saraswat to AMD and especially in this hall for giving a very good address which we were waiting from long time. Indeed, sir, it's a very important moment for AMD and INS. Probably for the first time, this type of lecture is being arranged in a series, and this lecture is going to be the last lecture. We initiated this series some 10 months back, and this is going to be completed today, that is 1st of July, and by the end of this month, we are going to complete the memoir which we promised that out of this series will be ready, and probably on 15th August, the memoir of all these lectures is going to be printed, to be distributed, and will become a history and historical document. So sir's lecture is going to be the last lecture. Though we are requesting him to come, and physical presence was necessary, and that's why we could get today. Dr. Saraswat is associated with many projects with the Department of Atomic Energy, and especially with AMD. His guidance has given us a lot of enthusiasm and direction for way forward. His positive thinking and catalytic action, which drives any department, was benefited to us, and we have enjoyed the directions receiving from him. At this moment, our secretary, who usually is available in virtual mode, but because of certain preoccupation, he is not available, and he conveyed to me that you expressed my feeling that I am always with such type of lecture series or such type of programs. And this is his guidance that we initiated this lecture series, especially asking the Padma awardee to give their views. So 10 Padma awardees have already contributed, 9 Padma awardees have already contributed. Today we will be having the 10th one, and various aspects have been covered, starting from space, starting from nuclear energy, from many biotechnology, many subjects have been touched on this lecture series. And all those things are available. It was requested, it was demanded rather, that all these things should be available even for post-lecture viewing. So anybody who is interested, who could not come, who could not attend virtually also this, he can see the lecture in YouTube later at his convenience. And this lecture series is widely publicized. Many are connected through YouTube. Only webex data is here with us, but many are connected through YouTube. That would be in hundreds. Since AMD has got a presence in pan-India basis, I mean, all over the India, and all those headquarters have propagated to the school, to the college, and to the technocrats, those who are associated with us. They are all seeing through YouTube. A large audience, I am expecting 200 to 300 audience are available with this program. So I welcome all those virtual audience who are attached with us and the physical audience for a very good lecture, very rewarding lecture, knowledgeable lecture, which we are going to have from Dr. Saraswat. With this word, I am looking forward for a nice interaction with sir, and half an hour session is also kept, who the students can interact with the personality. I mean, that type of chance is rare, but we have arranged that the students can ask any question to Saraswat sir, and I know he responds very well, and we would like to listen that response. We would like to witness that type of response, which is going to be a very, very knowledgeable item of this series. Thank you.
Thank you, sir. So before we invite our speaker onto the stage, I would like to introduce him, though he is a very renowned person, but for the benefit of our students and faculty members from different schools and colleges, and all those who have joined us online, I would like to introduce Dr. Saraswat. Our first Prime Minister, Dr. Jawaharlal Nehru, once said, and I quote here, "Future belongs to science and those who make friends with science." So today we have a personality who made friendship with applied science and converted them into many technologies. So it's my pride privilege to introduce today's speaker to the audience. Dr. Vijay Kumar Saraswat completed Masters in Engineering from Indian Institute of Science, Bangalore, and PhD from Osman University, Hyderabad. He is a gifted scientist with vast experience in defense research in both basic and applied sciences. Dr. Saraswat retired as Secretary, Defense Research and Development Organization, DRDO, after more than 4 decades of service. Presently, he is a member of NITI Aayog. During his illustrious career at DRDO, Dr. Saraswat has been credited with indigenous development of missiles, namely Prithvi, Dhanush, Prahar, and Agni Fire. Initial operational clearance of light combat aircraft, Tejas, and nuclear submarine, INS Arihant. As Secretary DRDO, Dr. Saraswat played a pivotal role in development of various technologies. He has also worked as Homi Bhabha Chair Professor in DAE and as a consultant in many other departments, including NTPC, IOCL R&D, and conceptualized the setting up of Indian Railway Research Institute Presently, Dr. Saraswat is also the chairman of Research Advisory Council of IOCL R&D. Dr. Saraswat initiated a program for development of silicon photonics technology by setting up Photonics Valley Corporation in Telangana. It is a government of Telangana initiative in collaboration with Photonics Inc. USA. This will have large impact on the upcoming 5G and supercomputers. As member NITI Aayog, he has initiated a program to develop methanol economy for transportation, energy generation, and production of chemicals and fertilizers. He has chaired a committee for shaping roadmap for Make in India in body armor and for release of Indian standard on body armor by Bureau of Indian Standards. Dr. Saraswat led an empowered technical committee, advisory committee for the development of national supercomputing systems. The nation has conferred him with many awards, and most notable among them being Padma Shri 1998 and Padma Bhushan in 2013. With this brief introduction, let me invite Dr. Saraswat to deliver his talk. Sir, please.
Slide. Pointer अलग, slide changer अलग. So I have to use two devices. हाँ तो जिसको use करेंगे ना. हाँ ये ठीक है. And this is a changer slide. Okay. Very good afternoon. Namaskar to all of you. Dr. Sinha and all the distinguished scientists, engineers, officials of AMD, and those who are on the virtual platform from different departments of atomic energy, the members of the industry. I see the CMD, CIL being here. And of course, I see very young friends from different schools, the boys and girls, who are making this place much more beautiful. I have been planning to come to AMD for a while. Myself and Dr. Sinha have met a couple of times on various meetings discussing either rare earths or atomic minerals or many other things. But every time Dr. Sinha has said that, sir, you have to come to AMD. By the way, I live in Hyderabad, used to live in Hyderabad from 1972. So it's almost 50 years of my association with the city of Hyderabad. And, but from 2005, mostly I'm in Delhi. So it's almost like coming and going. So I said, one of the visits to Hyderabad, I will come and visit AMD. But because of COVID, I think we lost a lot of time. And we once thought of doing it virtually, but I thought, no, virtual discussion may not be very rewarding. So I decided to keep it on. And this happened on a very short notice. It was just that I was coming and I said, no, I will. I just landed at 12:30 and I said, I'll drive directly for AMD. So this is the only way we could manage. So thank you very much for accommodating me with all my limitations. I would like to mention that you must have heard in my introduction that I was working in Department of Defense. So my main area of work was what we call as missile development, missile technology development. Almost for about 40 years I was involved in doing propulsion systems and missiles, different type of missiles, Prithvi, Dhanush, Prahar, Agni, and ballistic missile defense protection system. And later on, we also got engaged into other weapons and equipment like aircraft, submarines, and so on. Because that's the way you grow up in the organization. But after my departure from DRDO, my focus has been on energy. As Homi Bhabha Chair Professor and consultant in IOCL, my basic work started on energy. Not that I never thought of energy earlier. Even when I was in DRDO, I wanted to do coal gasification. Mixed, actually, it was biomass plus MSW plus coal, the entire thing. And we wanted to set up a plant. But for various reasons, we did not succeed. But a lot of studies were done. And we could even produce a report and submitted that report to Dr. Chidambaram, who was then the principal scientific advisor. Taking clue from there, then we started, as I came to NITI Aayog, that became my major area of work. So today's topic, what I've thought is, in the context of what our Honorable Prime Minister has committed in the latest COP summit which took place, where COP26, he has announced that India will have net zero carbon. Net zero carbon means we will not be producing any carbon products in the atmosphere by 2070. Now, I see a lot of students here, youngsters, boys and girls, so I will have to explain to that. Today, whatever energy we produce from the fossil fuels, we pollute the environment because when these gases are emitted in the atmosphere, they contain carbon dioxide, carbon monoxide, methane, particulate matters, greenhouse, they are called greenhouse gases. And even the vehicles which are being run, most of you are coming by scooters and cars and all that. You are polluting every day. And that is where the atmosphere percentage of carbon dioxide is increasing by the day. Today, if you say 1875, whatever was the carbon dioxide level, from there we have come to almost 440 ppm today. And if we go beyond this now, then it is going to be disastrous, because more and more carbon dioxide, if you go, it raises the temperature of the atmosphere. And this rise in temperature is called global warming. And the impact of that you are seeing today in its big way. What are the impacts? You are seeing the variations in the climate. You are seeing either excessive rain or excessive heat. You are seeing melting of glaciers. You are seeing oceanification, acidification of the oceans. You are seeing biodiversity being hampered. And all this is demanding more and more energy, because today industrial growth is taking place, development is taking place. You need more and more energy. So you use the same methods of producing energy using either coal or natural gas or anything. Then what is going to happen? It is going to produce more of such emissions, and you are having a problem. That means there is a need for us to do what is called a change in our methodology of producing energy. Because energy has to be produced, because energy consumption is one of the indicators of growth. If you compare our energy consumption today, our energy consumption is about 1200 units per person per year. Whereas the developed countries like America, Japan, Germany and others, they are using 5,000 to 6,000 units per person per year. That means the industrial activity in that country is so high that the energy consumption is high. So that is an indication of growth. Now, if this is an indication of growth, means we can't say that we are doing something wrong by increasing our demand for energy. So that is why we have to meet the demand for the energy, but we have to also produce energy in a manner so that it does not give this kind of global warming. So today's topic is basically, with this background, I am now going to tell you what is that we are going to talk to. If you see today, we have produced energy by various methods. This doesn't change here. Is it changing? This one?
Yes.
It's off, right? Mm-hmm. Then you have to change. I will say next and you can change, okay? you have to be, can you change? Yeah. So, if you see what is happening to our energy scenario today, energy, when I started giving lectures on energy in 2015 and today is 2022, this number was 265 gigawatts in 2015. Today, this number is 402 gigawatts of energy. That means this is the installed capacity. And this installed capacity has happened because of the demand which has increased. Now there are various forms of energies which are being produced. For example, you take first major energy. You see this curve? This is the major energy. 60% of our energy comes from the thermal power. And what is thermal power? These are the various plants which are using coal or gas for producing electricity. This is the one. Then 12% of energy comes from hydels, all these your Nagarjuna Sagar or Srisalem and these kind of plants where hydel energy is being produced. The renewable energy has come into the last about 15 to 20 years in a big way, and these are photovoltaic cells which are actually converting the solar energy into electricity, and that's about 12%. There's another one which is called wind. You have seen those windmills running when you travel on various streets. They are also producing energy, and that's about 10%. The other thing which is happening now which is coming as part of the renewable because it can be reprocessed, is the bioenergy. Bioenergy is anything which is biological in nature. For example, the cow dung, the agro waste, the municipal solid waste, what you create, food waste which you create in your house, the food which you don't eat and just throw it off. All this is having a lot of energy that can be converted into the biopower. And of course, small hydropowers are there. And this place where I am standing today is responsible for providing the nuclear energy for the country. Nuclear energy is the energy which is released by the fission of the atom. Atom, if you are able to break, and then you do fission reaction, you get nuclear energy. Now, see, this is the kind of distribution what we have today. Unfortunately, except for this segment which is the thermal power, and to some extent others are not so much polluting. This is the segment which pollutes maximum. So we have to now see how to get out of this mess. Next please. Between 1950 and now, that's 2020, this is the installed capacity of various types of energy production devices. The highest, as you are seeing, is 236 gigawatts thermal. Then you have renewable is about 113 gigawatts. Then you have hydro, which is about 46.7, and nuclear is living at a very low level today, which is about 6 almost. So you see, while we should be doing this much better to reduce the carbon intensity, but this has been the main source of providing energy. Between 2010 and 2020, see the kind of slope change on this curve. That means the demand went up and we kept on adding more and more thermal power plants in the country, and as a result, we have this kind of a scenario. Next please. Now, as I was mentioning to you, when the energy is produced, it becomes important for us to make sure that it does not give greenhouse gas effects. And so there is a trilemma, what we call balancing the energy trilemma. Energy security. What is energy security? For all my demands, industrial demands, domestic demands, transportation demands, all my demands, I should be able to produce energy and provide it to the user. So effective management of the primary energy supply from domestic and external sources, reliability of energy infrastructure, and the ability of energy providers to meet current and future demand. That is the energy security. Energy equity. It should be available to all. It's not that energy is available only to industries or it's available to only, everybody should be able to get. So accessibility and affordability, it should be affordable at some price. That is why various governments keep on subsidizing energy so that it is affordable to each consumer. Then you have environmental sustainability, which is the third triangle, which encompasses the achievement of supply and demand side, efficiencies, and the development of energy supply from renewable and low carbon sources. As I mentioned to you, the biomass and other places, the low carbon sources, nuclear energy, they are all low carbon sources, not polluting the environment. Next please. This is the trilemma which we had to look at. In this context now, how does the nuclear energy play the role? That is the whole idea today which I want to discuss with you. If you see, you know about nuclear energy because you have been explained, you are all coming here, children have been also exposed to what work is being done by atomic energy, maybe something I will be repeating also. But the point is nuclear energy is the cleanest form of energy. So if you see, does not require the burning of fossil fuels. It contributes to the, does not contribute to the greenhouse gas emissions. So it does not affect the climate change. So it is the best strategy for energy transition. World over it has been recognized that nuclear energy is the best strategy for transition. Of course, there are naysayers for this statement. Many people who are anti-nuclear, they have their own views with respect to radiation, with respect to reprocessing of the waste and so on and so forth. But notwithstanding that, if you are looking at this, the climate change, I think there is no other method but to nuclear energy. More advanced reactors could be the key to providing cheap and plentiful nuclear energy. What we are doing today, I think if we can make more advanced, then we will be able to reduce the cost. For that, I have been talking about it, that small modular reactors which would require less investment than traditional reactors and could be contained on ships, making them relatively mobile also. SMR they call it. We will discuss more about this. What is SMR? The proponents of these small reactors have claimed that they would be particularly useful for smaller energy purchasers. Suppose you want to provide energy into a remote area where there is no other method. These small modular reactors can be taken there and installed, and then they can provide energy to everybody. So this is the kind of thing which is required as far as, that's why nuclear energy becomes useful for transition. Next please. It is easier to stockpile uranium than natural gas. You have been keeping uranium in your plant, you know how to keep it. Natural gas requires huge reservoirs, large, first you have to transport it in the form of LNG, then you have to convert back into gas and so on and so forth. More reliable in extreme weather events than some other sources of energy. So nuclear energy will feature in the global energy mix for decades to come, but its share in the mix and its rate of growth will depend on these factors. How fast we are in the innovation in new nuclear technologies. Why I am saying that? The era of large nuclear reactors, gigawatts, hundreds of thousands of megawatts and a few gigawatts, I think slowly it is fading off for various reasons. So the speed of innovation in new nuclear technologies. Then of course policies on legacy waste management. That is one area which bothers many people. So we have to find better methods of doing waste management. Market design and financing structures. In fact, one of the major reasons why we are not in a position to augment our nuclear energy production and setting up more nuclear plants is basically this: market design and financing structures. If you need to put up more plants at a faster rate, there should be a market for that. That means purchasing power for that electricity should be there. Number two, you should be in a position to finance those projects adequately at the right time in the right proportion. If you don't provide the money at the right time in right proportion, then the plant which is going to take 7 years or 8 years to be set up may take 20 years to set up. And then people will say, no, nuclear energy takes a lot of time. It is not nuclear energy plant which takes a lot of time to set up. It is the mechanism, it is the policy framework, it is the financing structures, it is the market design which is responsible for the speed of this. Besides, of course, management of the projects, which is very important. But this is the main factor. Nuclear energy is and can be one of the most cost competitive low carbon options. Lifetime extension of existing reactor is one of the best power generation investment. This is what we can achieve through this. Next, please. Now, what is the impact of each one of them? If you compare, as I was telling, each one has got some impact on the climate. This is where it takes. Nuclear power plant generate electricity through fission without any fossil fuel, we mentioned. This is the grams of carbon dioxide per kilowatt hour of power. If you take, and on these are the types of energy producing devices. You take coal, this is the highest, it gives you the highest percentage of carbon dioxide. Then comes biomass, then comes natural gas, then comes again biomass. And you see nuclear, where it is sitting, it is practically not. Then wind offshore and wind onshore, these are the kind of thing. So we are in this zone today. 60 gigatons of CO2 emissions reduced by nuclear power plants over the last 50 years. This is not our figure, this is global. As a result, nuclear power has one of the lowest average life cycle CO2 emissions among other energy technologies. Next, please. This is as far as the emissions are concerned. Second one is how much space is needed in setting up the nuclear power plant. You see this. One of the lowest land requirements of all carbon new sources. If you take a nuclear power plant, it takes about 1.3 square miles. If you take a solar plant, it is 75,000 more space. If you take a wind farm, it takes 360 times more space for the same amount of electricity, about 1000 megawatts of electricity. That means the area required tomorrow, for those who say that we will have more and more solar power plants, one has to understand that to have the same 402 gigawatts, if I have to do by solar, I need to have in this ratio the area of the land which is required. You won't have place for agriculture, you will have place for living, you will have only solar farms. So you have problems. So we have to have a combination. Next, please. Reliability. Nuclear energy is highly reliable. 92.5. This is what run at maximum capacity, 92.5 certain time during a year. These are some of the figures which I have taken globally. You take geothermal, it's about 74.3. Natural gas, 56.6. Hydropower, 41.5. Coal is 40.2 and 35.4. And solar is only 25%. Why solar is 25%? Because the vagaries of the sun. You have sun only 6 to 7 hours in a day. And out of that only 4 to 5 hours is the time when you get substantial solar energy. So that is the problem. So nuclear power plants are the most reliable, run 24/7. Nuclear plants run maximum capacity 92.5% of the time during the year. Next, please. What is the efficiency? Now we have to look at the process by which you are producing power, how efficient it is. You see this. Lowest structural material requirements. Nuclear power plant use minimum, whereas solar power plants use maximum material requirements. Useful life 30 to 80 years. Solar is 20 to 25 years. Wind is 20 years. These are one typical nuclear reactor is equal to 3.1 million solar panels. Is equal to 431 utility scale wind turbines. Can you imagine now? Do you still have a doubt? Where should we go? I think the answer is very loud and clear. Next. Safety. Many people say nuclear safety, big problem. In fact, so many times it is talked about. But the figures are quite different. Nuclear power plant maintain the highest standards of safety, security and emergency preparedness. Just one accident of Fukushima doesn't mean that it is unsafe. That happened due to what? The tsunami. But otherwise it was running as a beautiful plant. And in spite of that, the kind of damage it could have caused was much more. Because of the safety features which are there part of that, the damage was contained. Now you see deaths per 10 terawatt hours. This is a figure. In coal it is 246, for oil it is about 184, for biomass is 46, natural gas 28, nuclear is only 0.7, wind is 0.4, solar 0.2, hydro. Despite the conventional beliefs surrounding the dangers of nuclear power, it is one of the safest source of energy. That's why you see our Atomic Energy Regulatory Board and the safety boards of the Department of Atomic Energy, how rigorously they work on each and every design aspect of a nuclear power plant. The safety audit is done at least 3 times during the life cycle of the design to production. And then it is done along when it is running from periodically. Am I correct, Dr. Sinha? So these are the things which make it, people have learned how to manage nuclear energy safely. That is the way we can say. Next, please. Now, this is what you know. With this background, where does India stand? Are we really geared up for this kind of a transition where nuclear energy can actually go into that thing? Your presentation, this is for the kids who have come here today. I think your department must have already told you about the 3-stage program. Let us go further. Next, please. We have the pioneer, father of our nuclear program, Homi Bhabha, who was contemporary to our first Prime Minister, Dr. Pandit Jawaharlal Nehru. And he had a very clear vision that India, global uranium deposition less than 1% in India, but we have 21% of thorium. So we thought that he was that's why he formed the basis for our nuclear policy. And that policy was a 3-stage policy program which Bhabha Atomic Energy has been following today. Next, please. This program, this slide, probably you have been running it in your plant. These are the 3 stages. The first stage is a pressurized heavy water reactor which uses natural uranium, and you get depleted uranium and plutonium out of this. All this is fed into the second reactor called fast breeder reactor, where a non-fissile material, thorium is a non-fissile material. You understand non-fissile? Not means even if I do anything with this, it will not create fission reaction. It has to be made fissile by a certain process. So thorium is that. So fast breeder reactor is used. Then this gives you, this of course is a recycled inside. This gives you uranium-233, which is an isotope of uranium. So uranium-233, when it is put inside a thermal breeder along with thorium, then thorium becomes fissile and you are able to get the same fission reaction, and this becomes again within the system. We want to reach here. We are here at the moment. You see, we have to do this. This work is going on already in IGCAR, and this work is a few, I would say, I don't know how many years away, because I've been listening number of days for, statements on this, but this slightly away as far as I'm concerned. Next, please. In India, we have how many plants? This is the status. Whether this is adequate to meet our requirement. I showed you a picture, we are only 6.8 gigawatts or something. Next, please. We have 7 major plants which are there. Tarapur, Rajasthan Atomic Power Station, Madras, Kaiga, Kudankulam, Narora, Karpara, of different capacities. These are the capacities, and that's why this total becomes 6.7 gigawatts. These are the 7 plants which are operational of different kinds of technologies. Next, please. And these are the plants which are under construction today. Kakrapar Atomic Power Station of 1400 megawatts. Rajasthan again another 1400. Kudankulam 2000. Gorakhpur Haryana Vidyut Yojana, you got 1400. And this is about Bharatiya Nabikya Vidyut Nigam. So with this will give us another 6.7 gigawatts. That means over a period of time, maybe another 5. These are the time schedules which are already, some of them have passed, but maybe by 2030 we will have this 6.7 also added to that. So from 6.7 at about 14 gigawatts of power, or 13 point something gigawatts of power you will have. This is not going to be adequate. This is my worry, that this work which we are doing today and that 6.7 is not going to be adequate, because what I showed you as 402 installed power, by 2030 that will going to touch to 600 and odd. So the percentage wise you will still remain low. That means there is need for us to accelerate the setting up of these plants and also adopt newer technologies. Next, please. So what is the next? The newer technologies. what we are today using and what are the newer technologies which are available. The nuclear power plants are now called generation 1, generation 2, generation 3, generation 3 plus and generation 4. And 1950 to 60 was generation 1, then this became generation 2, and this is generation 3. Generation 3 is this one. So essentially people are going, we are in this mode now, commercial reactors, pressurized water reactors, boiling water reactors can do and all that. Generation 3 are our FBRs. Generation 3 plus 1 are light water reactors, and finally generation 4 will be enhanced safety, minimization of the waste and better use of the natural resources, more economical, improved proliferation resistance and physical protection. And in between now, 3 plus 1 is introducing world over is small modular reactors. And small modular reactors are going to completely change the as far as the scenario in the 4th generation of the nuclear reactors are concerned. Next, please. Now, what are the technologies which have been used? Some of you may be able to understand, kids, but this is for those who are into the field and they are already practicing this. The 4th generation systems are sodium cooled fast reactors, which is a neutron spectrum fast, which uses mixed oxide metal close, coolant temperatures run into 5 to 500 CD, and of course use powers anything between 300, 600, 1500 megawatts equivalent of electricity. Efficiency is about 42%. Then there is a very high temperature reactor, which is thermal, which uses coated particles as far as the fuel is concerned, and high temperature, they run at up to 1000 degrees, and efficiency is good in this case. You get 47%. Then gas cooled fast reactors, here this also carbides, here you use carbides, 45 to 48%. Supercritical water reactors, 50%. So all of them can be used. And the last one is the molten salt reactor, which I have been requesting that BRC should do something on this quickly, and which is about 700 to 1800, 45 degree. But the future is looking for alternate fuels also. As I mentioned to you, fossil fuels have to give way. It is not just the energy production, but transportation and any other things. So hydrogen is becoming a fuel which is going to be least carbon polluting. So hydrogen production is done by the electrolysis of water. That is called green hydrogen. Now green hydrogen will become green if the grid from which you are taking the power is also green. And how will the grid will become green? If it is powered by the nuclear energy, or it is not powered by the thermal energy. So what we need is some of these reactor technologies will be needed for the hydrogen production, and that's where we need to jump as early as possible. Next, please. These are some of the plants which are already existing. This is their floating nuclear reactor, which is already there. Nuclear torpedoes are, nuclear powered missiles are also there now. Nuclear submarines are there. We also have our own nuclear submarine. We have 4th generation nuclear reactor, which is the first available here in the globally these pictures. Next, please. So summary is generation 4 systems are being developed worldwide. International forum was established in 2001 and provides an international framework for development of generation 4 systems. Collaborative projects started with significant R&D investment worldwide, France and Russia, and VHDR China. Much still needs to be done before Gen 4 systems become a reality. Continued R&D, develop advanced research facilities, engage industry on the design of Gen 4 reactors, and develop the workforce for the future. Although BRC has got an excellent training school, you every year train a lot of people, but I think the research activity which is needed to be done to reach the level of excellence as far as Gen 4 technologies are concerned needs to be harnessed more. More investment is required, more people have to be trained in that area to give you that kind of a thing. Next, please. So, nuclear and the renewable. As I mentioned to you, renewable is carbon free, like the solar energy, less carbon, wind energy, less carbon, biomass, less carbon. Along with that, because these are not continuous power supply systems, we need to feed nuclear energy. Next, please. Next. So energy demand 2019 to 2030, I was just mentioning to you. Before pandemic, our indication was that we will go up by 50%. After that, we have stated policy scenario is that we will go up by 35%. But there is another scenario which is called sustainability scenario. That means you want to make sure that your carbon dioxide emissions are minimized. The rate at which it will happen is only 5%, sustainable development scenario. Additionally, then it needs to reach at HDI, the Human Development Index, are highest in the world. Our requirement highest. Climate crisis is here and India needs to deep carbon emission cuts very quickly. That's why our Prime Minister has said 2070 we will have a zero, but 2050 we will be able to come to at least less than 30%, 20%, that kind of a thing. Deployment of clean energy, decarbonization as well as growth is one of the biggest challenge. That is where we have to come together. Okay, next please. Now, how much is the share of nuclear power in the renewable sector today? This is nuclear. 2010 we were 2.8%, then became 2.2, now it's 2.2 in 14-15, then 1.8, 1.9, 1.8. So it's coming down. Why it is coming? Not that the reactors are coming down. The total demand is going up. And renewable is going up. What was 9.8, today it is 24.3. That is the kind of improvement. So our focus has been on renewables as much as possible. But alongside, our focus is on nuclear also. That's why I showed you the picture of another 6.8 is being done. And we have a program of pressurized heavy water reactors where we want to build 17 to 18 in a fleet mode, the heavy water reactors. So that will be our, because that's the technology which is now completely indigenous. Industry is well equipped to do the job. It's a question of putting the right marketing philosophy, financing structure, and making sure that we have the necessary resources to set up those plants. One of the major areas which is going to come in the way of these plants, and Dr. Sinha is sitting here and many of you are working in this area, is the availability of the fuel, the uranium. India, as I mentioned to you in the first slide where Dr. Bhava has mentioned, we have less than 1% of the uranium resources. So if we are to run these plants, we need uranium. And that's why the work of the AMD is very important. Nuclear Uranium Corporation is important, that we have to get more and more uranium. Otherwise, we'll have to import that, which is not a good sign, because people will say instead of importing fossil fuel, which we are doing today anyway, lot of gasoline, lot of crude we import, we are importing uranium. Of course, they don't realize that the investment on the crude import is 1,000 times more than the import of the uranium. That is a kind of, one has to look at the magnitude of that. So this is what is happening. So it is important that we have to play a major role. India also has got reserves. In fact, today only we were discussing with Dr. Sinha. In Rajasthan, in Karnataka, in Andhra Pradesh, in Telangana, many places we have got good reserves. But somehow some view has been found among the people, and that's why it's very important for us to actually deliver the right message to everybody, that mining uranium is not harmful for anybody. It does not cause any health hazard. It does not pollute water. It does not create any problem of radiation. And so we should get out of this kind of a thing and do not come in the way of stopping the of uranium mining, which is happening in many states. And you as children today should tell your parents, tell your friends that if India wants to really be a good carbon-free nuclear energy power, we have to allow the mining of uranium across. Next, please. So, target is today 20,000 megawatts, revised in October 2020, 63,000 by 2032. Am I correct, Dr. Sinha? This is what we have done now. Total achieved capacity 6.7, total projected capacity 22.48 gigawatts by 2030, and total projected capacity by 2047 is 54.3. Best case scenario it is. And total planned projected by 2025 is 15 point, that is what I was giving you, 6.7, 6.7, that number. What are the major contributors to this gap? You see the gap now. The gap is the recurring time and cost overruns. We were having a review in NITI Aayog on the nuclear energy build up in the country. We have always a lot of people saying we should stop nuclear energy program. This kind of a thing happens. Then you all know that it cannot be done. So they blame that time and cost overrun is the reason for stopping. I said no. I've been saying time and cost overrun is visible figure. But you should go into the reasons why the time and cost overrun has taken place. If you don't analyze the reasons thereof, then you will not be doing the right decision. You will not be taking the right decision. Every project, if you analyze of the Nuclear Power Corporation, you will realize that while the plants have been sanctioned, cabinet sanction has been obtained, but most of the time the funds are not made available. Most of the times the clearances are not given by Environment Ministry, the state government, the land is not made available, and variety of factors which are beyond the control of the Nuclear Power Corporation. Factors which are under the control of the state governments, factors which are in the control of the Finance Ministry, factors which are under the control of the legislative authorities in the various state governments. So these are practically, we are pleading with the agencies to allow us to work. And in that scenario, if there is a time and cost overrun, I think that's not a blame that should be given to the people who are doing the job, but to the system which is responsible for this. So this, however, is a common issue which needs a, and by the way, I think many of you must have visited foreign power plants and seen the history of how much time it takes for any nuclear power plant to set up even abroad. I think the figures run into 12 to 15 years at any other place also. Am I correct? So we are nowhere bad or worse. Next please. What are the challenges? Prime Minister has mentioned in his speech that PM set a goal for India to achieve energy independence by 2047. What is the meaning of energy independence? No import of the fossil fuels. And that's why he said we'll go into solar, we'll go into wind and majority of things. But to meet this goal, target and achieve nuclear power is one of the major challenges. Rapid scale up and the adoption of nuclear energy. We have to do this. Private participation in nuclear power generation. See, thermal power plants, we have given private participation. We have given private, solar power has come up because of public-private participation in a big way. In fact, if you see, majority of the solar installations are private participation. So why not private participation in the nuclear power? I think this is the question being asked to me also in NITI Aayog many times, and I have been reverberating the same thing with the Atomic Energy Department. Other than the safety regulations and the safety and the regulatory requirements because of the strategic materials being handled by them, I don't see any other reason which is coming in the way of allowing a private company to set up a nuclear power plant, provided he does not compromise on safety and regulatory issues. Accelerate development of indigenous SMR technology. I think many of you have heard me earlier also. I gave Shekhar Basu memorial lecture. At that time also I had mentioned this. We need to give indigenous SMR as early as possible. Long-term energy strategy is what is needed. Next please. Private participation I want to touch upon. Next. If you see long-run price of electricity, although cost of variable renewables is steadily declining, this slide was shared by me, Dr. Kakotka shared this with me, so I'm just giving you that figure. All of us know that variable renewable energy, the prices are declining. You know, today we have touched almost 2 rupees a unit and things like that. But MIT studies showed that pairing them with steady carbon-free source such as nuclear is a less costly and lower risk route in a near zero emission scenario. This is I won't go into details of that, but the fact remains that for various power cost of this, you are able to lower cost of electricity to end users is the key. Therefore, large scale nuclear power in India, a few hundred gigawatts is essential. This is the summary MIT study has given. So this is substantiated by the modeling which they have done with various resources and things like that. So lower price. Now, what is the price of power from thermal power plant at the doorstep of say NTPC unit? 3 rupees 20 paisa. NPCL, suppose it produces at Rajasthan or someplace, is 5 rupees 40 paisa. Am I correct? This is of that region. Now this 3 rupees 20 paisa is also with subsidized price of coal. If you get the coal price to thermal power plant at the same price, you will not have the same. So if you compare apple to apple, you don't find any difference. But these are the factors which nobody talks. We only talk in our reports, this is 5 rupees, this is 4 rupees. So this is costly. We have to go into the nitty-gritty of costing process. Next please. So need for privatization, insufficient to meet the goal of several hundred gigawatts with the prescribed time of 247. Too large for the government alone to undertake this kind of work. So it is the best that we accelerate. The role of government is to accelerate the fleet mode construction of 700 megawatt PHWR and augment 3 more fleets before 2050. Right now we have 1 more fleet, 17 as we are seeing. We are recommending it should be 2 more extra to be added. Create a conducive policy environment with interventions like nuclear power purchase obligations and must run state. This is another thing. You produce power and you don't have purchase power obligation. Solar power today, 25 years purchase power agreements state governments are signing. But why not for nuclear power? They should find, and they will give you 24/7, whereas that fellow gives you only 5 hours a day. So we should get that. Improve and empower management structure with decentralized decision making and synergy with energy, PSUs and industry. This is a very important point. All the factors which I talked about, time and cost overrun, are actually embedded here. Decision making process, empowerment to the nuclear power corporation, to the scientists, to the people who are managing those PSUs is most important. Role of private sector is very important. I personally believe that we should now invite the private sector to do build, operate and transfer models, like we have done in the case of solar. In case of different foreign reactor technologies used, ensure significant domestic manufacturing. Suppose a company goes and gets a plant from outside. We should ensure 2 things. The design should be actually vetted by us so that we get the safety requirements taken care of. IP should be held here, and then all the manufacturing of the critical parts should be done indigenously. That process will ensure that our dependence on import is minimum, unlike what is happening today in many of the other sectors. Cooperate and collaborate with the government in continuing R&D and implementation of the 3-stage nuclear program. This is so many people have even criticized this. Even I used to criticize this once upon a time, because I used to say that, are we going to wait for uranium-233 for indefinite period of time to get my huge resource of thorium to be utilized? But then I realized the complications of the FBR and what we are doing today at IG CAR. It is happening, but there are alternate methods of making thorium as a fissile material. The accelerators being used for making the thorium as a fissile material. Why don't we try that? Can we do that? Has anybody studied the economics of that or the equipments required for doing that kind of a thing? Will that be a right process, or shall we continue to wait till the uranium-233 comes out in adequate quantity and we start our thorium reactors? So this is a very important point. Cooperate and collaborate with government in continuing R&D. Next please. Otherwise, economic key challenge is economic viability. The price of electricity needs to be low enough for the consumer to buy it. This is one. Human and environmental safety, I mentioned that. AERB regulations and IAI safeguard must be implemented. Market accessories, a competitive economy can only be achieved if there is an initially assured market large enough for the private participant. Why the solar energy picked up? Because there was a market. The cost came down because of market. What was 17 rupees, 18 rupees in 2014-15, within 5 years it's crashed down to 2 rupees. So that is a kind of a thing because of the market. Same thing can happen here also. Technical skill and experience should be there in the private sector. If it is not there, then you run into problems. Corporate affairs, structure of the private participant may evolve and change over the life of nuclear power plant. Merger and acquisitions I am talking of. So that becomes a problem. Public opinion, of course, is very important, because they say private, whether it will handle or not handle. Next please. So the solution to these challenges requires innovation in both technology and policy. The key technology here is, for that, small modular reactor. Instead of giving to the private sector large reactor setting up, if we give small and modular reactors, it will become a much manageable situation. Next please. Now what is this SMR technology? SMR technology is, next, it is also a small reactor, 300 megawatts of electricity instead of traditional 700 to 900 megawatts, built remotely in factories in modules rather than on site. Of course, this also relies on fission. Next, the World Association, Nuclear Association and International Atomic Energy Agency has given large reactors are 700 megawatts, medium 300 to 700, small 150 to 300, very small is less than 150 megawatts. This is the classification of SMRs what we are talking of. Next please. Now how does a SMR work? This is good for the kids at least. They will realize how the SMR works. Actually, a nuclear power plant generates heat through nuclear fission. That means when the neutron goes and hits that, it splits and the energy is released. So the process begins here, core, the heart of the reactor, where heat is generated by nuclear fission reaction. After that, there are control rods used to control the power of a nuclear reactor, including shutting down. These rods are pushed forward, backward. Then there is a steam generator. The heat is used for generating steam in secondary loop in the steam to drive a turbine. You run a turbine with this steam turbine. Then there is a reactor coolant pump which keeps the temperature under control, and of course pressurizer with coolant water under high pressure to prevent it from boiling. It looks so simple, no? Don't you think it looks so simple? But it is not so simple what you are seeing. There are a lot of complications, but the fact remains that reactor core, the control rods and coolant water pump and steam generator and all these things, they have to be compact and put it into place with all the safety inputs inside. Next please. So a nuclear option to meet the need for flexible power generation for a wide range of users and application. It is economic, lower upfront capital costs, economy of serial production, modularization, flexible application, smaller footprint, replacement for aging fossil and fired plants it can replace, and potential hybrid system. So it will give you better affordability, shorter construction time, wider range for users, site flexibility, reduced CO2 production, and integration easily with the renewables. That is what SMR can do. Next please. Now worldwide, what is happening SMRs? Who all is doing work in the SMR? These are the countries who are already working in the development of SMRs. Argentina, Korea, Russia again, China, USA, Empower. New Scale is one which has come fairly advanced as far as the development. Westinghouse, China again, Japan. So these are various countries which are already in the advanced SMR. Why I am using the word advanced? Because most of them are using the Gen 4 technology. Gen 4 technology. They are inching more and more closer to that. Next please. There are 100 designs of SMRs under 4 general types. For example, type 1 is boiling water or pressurized water reactor, where the coolant is light water, lightly enriched uranium, 2 to 5 years typical refuel signing, and 374 degrees centigrade pressurized load technology, risk is less. High temperature gaseous reactor, helium or carbon dioxide, graphite modified, enriched uranium to 20%, thorium or pebble type fuel replaced continuously 5 to 10 year cycle, capable up to 700 to 950 degrees. Liquid metal fast breeder with sodium or lead or bismuth metal, enrichment needed, refueling cycle up to 20 years. This is the temperature limit. Molten salt, lithium, beryllium, fluorine salt, some designs use chlorine salts also, cryolite compatible. And this is the kind of burn and this is the kind of temperature which is there. So these are the technologies which are being tried out today as far as the SMRs are concerned. Next please. These are the designs, single unit SMR, use of well established light water reactor technology and fuels to provide standalone units that may replace small fossil fuel units. This is something what we can try. Multi-mode LWR SMRs, also technology may be either operated as a replacement for mid-size base load capacity or in distributed generation framework. Mobile transportable SMRs currently apply for LWR and are intended to be easily moved from location to location. Next, please. Next. This is LWR based are most actually mature. Gen 4 technologies use alternative coolants like liquid metal, as I mentioned to you, molten gas or salt, and different types of concentration compared to LWRs. The most mature Gen 4 designs are metal cooled, gas cooled systems with some units currently in operation under construction. These designs may also provide a specific opportunity to consider non-electric applications like high temperature outlet temperatures for thermal dissociation of water to produce hydrogen. That is the kind of thing. Next, please. By the way, SMRs are not new. SMRs have been used in submarines. 140 ships are powered by more than 180 reactors. 12,000 reactor year of experience. In the US, 6,200 year-on-year accident-free operation involving 526 reactors over 240 million kilometers. Trains, planes, and automobiles. So these are basically used. Even we in our own submarine are using something similar to SMR, which has been developed by our own Department of Atomic Energy. So it's not that the technology is not known. It's not that we cannot do it. Now it's a question of giving the right push and achieving perfection in terms of cost and time. Next, please. This is the new scale, as I mentioned to you. This is the most developed reactor today, which has reactor. As I mentioned, this is the similar thing: reactor vessel, pressure vessel, steam generator, pressurizer, and containment. Next, please. Now, what is the status of this? First SMR to undergo licensing in the US. You can imagine people say SMR is there in the market, why not we allow private? This is the status. Design certification in 2016, docketed and review commenced by Nuclear Regulatory Commission in 2017, and new scale received standard design approval in 2020. It is still not yet cleared from the point of view of its operation by the regulatory authorities in India, America. But there's a lot of work. The reactor has reached fairly high level of maturity. It will one day become available. My fear is, if such reactors come already in the market, then again we will have a problem, buy or make. And many of the private companies will shake hand and bring this technology in India in a blind manner, and then we will be continuously producing nuclear reactors without understanding, without indigenous content, without value addition. So it is important for the Department of Atomic Energy to give maximum push to this and get hold of this design into the market. Next, please. So large generation 3 and 3 plus, these are the factors. Small generation 4, these are the factors. These are some of the factors which are actually making the difference. Next, please. Now cost becomes very important. If you see the cost drivers, the factors which are reduced responsible for driving the cost from year to year and which will become large reactor cost here are modularization, design simplification, standardization, harmonization, lightweight, light water, economic drivers. These are the SMR drivers that can happen. So over a period of time, you will be able to get the cost figures comparable to this and this is what large reactors economy of scale is happening. As the numbers will increase, the prices are coming down. Next, please. There is a IAE, International Atomic Energy Agency platform on SMRs. IAE platform on SMRs and their application. It includes publication of technology roadmap. There are about 50 SMR designs and concepts globally at various development stages, of which 4 are in advanced stage. Construction in Argentina, China, and Russia. However, and this is the figure of January 2022. I am giving you this figure. None are commercially operational as on today. The technology, its safety and economic competitiveness must be demonstrated before SMRs can be more widely deployed. Panelists agreed. This was the panel which actually did a review, and this is the report I am quoting from that. Next, please. Indian SMR. 40 megawatt thermal fast breeder test reactor was built by IG CAR in technical collaboration with France. and the reactor design is similar to their Rhapsody reactor. The FBTR reached its first criticality in 1985. Maximum power level is 32, producing an electrical output of 8 megawatts. It is now ready for operation at its full rated capacity of 40 megawatts. Am I correct? Next. The design of the prototype FBR continued in IG car. The design analysis, prototyping and testing of all major components completed in 2000. Bhavani started the construction of its 500 megawatt fast breeder reactor in 2003, which is now about to be commissioned. First of its kind reactor, it experienced challenges during construction, installation like component development and critical reviews. All of you have been part of it, I don't have to go into that. Similar challenges during commissioning included many in-situ design changes will be faced. Pressurized reactor. Next please. So SMRs basically facilitated access to nuclear energy in new sectors and or regions, off-grid in remote locations, adaptation to site constraints, seismic and cooling sources, newcomer access to the nuclear energy. Decarbonizing energy system, replacement of aging coal power plants. What I am thinking is, in the next about 25 years, about 25 to 30 our thermal power plants are going to be wasted out. Instead of building new thermal power plants, if I can replace them with SMRs 300 to 300 megawatt capacity, I think this is going to be the right decarbonizing criteria. Non-electric applications, as I like district heating and so on. Complementing variable energy, wherever you have solar energy, and we are talking of storage of energy, solar energy using batteries, which is the most costly option available, which is requiring lithium, and lithium is not available in our country. Even if we recycle the thing, it is going to be a problem. So nuclear energy with this load following and fleet effect integrated energy system can be done with the help of SMRs. Next please. So advantages are, it can be factory produced in large volumes, it can be deployed even at a remote location, it can be operated in fleet mode, rapidly installed and commissioned, safety regulations can be standardized and easily replicable, redesigned and upgradation as well as technical training is feasible. These are the advantages. Next please. So nuclear for activating net zero. What is our long-term energy strategy? Next. Nuclear is a proven and effective low carbon energy source. It is available, scalable and deployable. It is flexible and affordable source of clean energy. Can deliver more than just low carbon electricity. Supports inclusive and sustainable global development. Next. This is what full potential of nuclear contributes to net zero. With conservative approach, there are two things mentioned here in this graph. One is a ambitious projections where SMRs post 2035, large scale new builds plan, long term plan, all are plotted. There is a conservative approach where instead of small modular reactors, market outlook only, not extrapolation, large scale under construction and so on. So the summary is, with conservative approach, installing a nuclear capacity of 400 gigawatts will avoid cumulative 30 gigatons of carbon dioxide. And I want to tell you, today, globally, we have about 42 gigatons of carbon dioxide released per year. If we had to bring it to 1.5 degrees Celsius requirement, which is equal to the pre-industrial area, we had to bring it to less than 20 gigatons per year. Now for that, this is the kind of strategy will help. With ambitious approach, installing a nuclear capacity of only 1160 gigawatts will avoid cumulative 75 gigatons of carbon dioxide, which is equivalent to 1.5 degree scenario. This is what I was telling you about. So over the past 5 decades, nuclear power has cumulatively avoided the emission of about 70 gigatons globally and continue to avoid more than 1 gigaton annually. This is what the present global scenario is there. So that shows that if we have to really reach net carbon zero, some of these scenarios we have to embed in our own planning process and accelerate the program of nuclear power production. Next please. Life cycle emissions from each of them. For example, wind gives you 11 gigatons of carbon dioxide per kilowatt hour. Hydropower gives you 24 gigatons of CO2 equivalent per kilowatt hour. Concentrated solar 27, geothermal 38, nuclear only 12, and then solar is about 48. You must be wondering what is this solar 48? There is no, but there is so much. This is called life cycle emission. Life cycle emissions are right from the beginning when the solar cell is actually produced using silicon, mining, this, that, everything that happens. That is these are until it is completely onto the floor. So that is the life cycle emission. That's why even nuclear has got some, because there are certain things which use, materials which you use, which are using carbon. So that's the reason. Even geothermal, which is supposed to be nothing but water, here also you have emission. Next please. So 3 surprising ways to use nuclear energy. One is nuclear desalination. That is over half of the emission-free electricity. 1/5 of the world's population experiences water scarcity, and the demand for fresh water continues to grow. Desalination plants around the world rely on energy to remove salt and produce fresh water. So this is, you know, in our Chennai, we have RO plants on the sea, but they are all run by the grid electricity, which is again carbon intensive. Next please. Clean hydrogen production. I was mentioning to you, green hydrogen has to be produced. So nuclear power plants can be used to generate clean hydrogen for use in fertilizers, steel refining, synthetic fuel or cargo ships. Process heating for industry, all the steel industries, cement industries and all that is carbon-free option to power industrial facilities and provide heat. For example, you take aluminum industry. Aluminum is produced by electrolysis process, all of them. We need huge power. They are power intensive industries. Why should I use a thermal power plant? If I put one SMR there, it meets all the requirement. A simple thing can be done. Same thing with the cement industry. Process as well as utility. Both of them I can replace by the nuclear power. Next please. What is happening in our own as far as nuclear hydrogen production is concerned? Department of Atomic Energy has launched a green hydrogen mission. This is India launch, of course. Options for nuclear assisted hydrogen production need to be considered. India may employ a closed nuclear fuel cycle with large scale thorium utilization. So this is a nuclear reactor. It can produce nuclear low temperature electrolysis and high temperature electrolysis to produce hydrogen, or a thermochemical hybrid cycle to produce hydrogen, or a thermochemical cycle where direct dissociation of water can take place at more than 1800 degrees Celsius to give you hydrogen. R&D activities in BARC are targeting challenging technologies for high temperature nuclear reactors using thorium based fuel and capable of supplying process heat at 1000 degrees centigrade. They have started a R&D program on nuclear hydrogen production through water splitting based on SI thermochemical process. Next please. There is a major advantage of nuclear energy is that it impacts our sustainability development goals. What is sustainability? Anybody knows? You children, have you been taught about sustainability development goals? No. Nobody has been taught. You come from 10th standard, 8th standard, 9th standard. 8. So sustainability is where we can live in this planet Earth without compromising the life livability on this planet Earth for the future generations. That is a simple generation. You use water and don't leave it for your future generation, that means it's not sustainable. You use energy and make fossil fuels and make climate warmer, it is not sustainable. Sustainability is where social and economical and environmental all factors are taken care of. So nuclear energy actually helps. 17 goals have been identified by the United Nations for sustainability. Out of these, some of the goals directly are affected. No poverty, avoid wasting food, irradiation can delay fruit and vegetable ripening, can control pests and prevent transmission of foodborne illness and so on. Good health and well-being, nuclear medicine, already BRC is doing wonderful work with the Tata Institute of Tata Cancer Research for this. Clean water and sanitation, SDG 6, I was just mentioning to you about desalination. Wastewater can be irradiated to transform chemical, reduce pollution. SDG 9, which is industry, innovation and infrastructure. Radioisotopes are used by manufacturers as tracers to monitor fluid flow and filtration. SDG 14, life below water. Isotopic techniques are being used to study the process and better understand the impacts on marine life. C5, life on land. Nuclear techniques can be used to improve soil quality, rewarding farmers with abundant and healthier crops. Next, please. So what is a long-term strategy then? What should be our long-term strategy? After listening to this, I think it becomes very clear. Long-term strategy addresses the several portions of the energy economy, includes roadmaps on the energy generation, mix, the economic demand, energy demand and their interconnect. Energy demand is usually in the form of a periodic cycle with some seasonal and regional. In winters you need less energy, in summer you need more energy. Like this time summer was very heavy. The demand for energy in Delhi was so much that the coal supply became a problem, and then we had to double the supply of coal using extra railway tracks and things like that because of the severe summer. So this is very cyclic. So at its simplest, the demand over the cycle can be split into the base load and the peak load. If your demand is divided into two, the base load and the peak load, given the demand, the energy mix must be determined to maximize utility of the resources. The best energy mix strategy for India, especially in the net zero emission scenario, is to use renewables paired with steady carbon-free sources like nuclear energy. That is what I want to submit. Next, please. So, use nuclear power as a base load, ensure a competitive economy and low cost to the consumer. Nuclear power purchase obligation should be signed. Independence and net zero emission in a sustainable manner can be achieved, and this can create additional interest and incentivize private participation in the nuclear sector, attracting private investment. Long-term strategy will contribute to increased R&D efforts towards the next stages of the three-stage nuclear program. I think this is one area which really needs to be accelerated. Next. So energy policy makers have an important role to play. I'm now coming back to the same point, that unless there is a policy framework, we will not be able to push this particular agenda of nuclear energy. For this, electricity market reforms are needed, robust and predictable financing framework is needed, international licensing framework is needed, innovation and investment in nuclear research is needed. Next, please. So, COVID-19 actually saw some very interesting figures. Nuclear power and the cost-effective decarbonized electricity system was achieved. Creative, high-value jobs in the post-COVID recovery with nuclear energy projects is happening. Unlocking financing for nuclear energy infrastructure in the COVID-19 economic recovery, this is also happening. Building low-carbon, resilient electricity infrastructure post-COVID-19 era is become a necessity. Next, please. So, therefore, the path to an energy independent requires, this is my last slide, SMR technology-based private participation and nuclear power as the base load. Next. Thank you. I hope I have not given you you already knew most of the things, so. Any questions?
Yes, sir.
Yeah.
So anyway, thank you for the scintillating lecture that we just heard from you. It covered many basics, applications and challenges, then a lot of solutions that you have provided ahead.
Use the mic.
Yeah. Yes. So basically, we would like to thank you for that. And first, before that, we have a few questions from the school students, and I have a list with me. Here, one student from Osman University, Habibuddin Issa.
Stand up.
You can stand up and ask before the question.
Good evening, sir.
Can you be a little louder?
Good evening, sir.
Yeah.
My question is, why India first did not accept the nuclear emission?
Keep the mic close to your mouth.
My question is, why did India first did not accept the zero carbon emission?
No, we have accepted zero carbon emission as our strategy. All of us have realized that's why in the last gathering of all the nations, which is called COP26, we have already committed that India will become net zero carbon by 2017. Now, If you are saying that why we have not said it should become tomorrow, that is because of that is the explanation I have given. Today, our 70% of the power is produced by thermal power, which is polluting. And if I have to replace that 70% of the power by non-polluting resources, I have to do a lot of work. And that work is in terms of setting up more nuclear power plants, setting up more hydel power plants, setting up more solar power plants, which takes time and cost. So we cannot do it overnight. So actually the strategy there, what we are saying is that the reduction can be done even when the thermal power plants are running. So for this, now NITI Aayog has already started talking about carbon capture, utilization and storage. If I can integrate capability to capture the carbon dioxide which is coming from the industrial houses like cement plants, steel plants, thermal power plants, refineries, they are the bulk producers of carbon dioxide. I can capture that carbon dioxide, convert it into usable chemicals or do the storage into geological formations, then I can reduce the emissions I will reach. So we have two-stage strategy. One is follow the CCU while the thermal power plants and all these industries are not switching over to non-carbon actions, and slowly go for adding more and more nuclear power, more and more renewable power, so that we have by 2070 net zero carbon production. Okay?
Okay. The next question would be from Bhavya from Saga School.
Good afternoon, sir. So as we know that this net zero mission was started up in Bhutan and the government wanted to complete this by 2050. But why did India took up the mission up to 2070? We have well developed technology out here. Why can't it complete by 2050?
What is this? Some Bhutan plant. Yeah.
Yes, sir.
2020 has been brought down to 2017.
They told that they would complete this by 2050.
It is postponed.
Yes, sir.
See, any postponement could be due to various factors. See, in any, I don't know the real reason, but I am trying to explain to you. When you set up a plant, there could be many things which govern it. Availability of material. COVID came for 2 years. There is a supply chain disruption. Today, whatever imported items you are getting from outside are not available because of supply chain restrictions from the foreign countries are coming. So many factors are responsible for delays that are happening now, at least post-COVID, whatever delays are happening. And even before, there could be delays due to environmental considerations, clearances not being given. So the real reason I do not know, I can't answer that, but these could be the reasons.
Thank you, sir.
Thank you. Then
आप जानते तो बता दीजिए. Yeah.
Earlier it was planned, so slowly it will be done.
Okay.
So considering developing nation, it is 20 years is enhanced. We cannot suddenly stop.
okay, next question would be from N. Navyasri from Udbhav RBL School.
So, sir, my question is, if any danger happens because of nuclear power plant, so how government is going to take action on it?
See, there are two things. One is safety by design. All our nuclear power plants, I'm talking of Indian plants, are designed for safety. Even if there's an accident, there's an automatic shutdown operations, and then there are mechanisms to reduce the emissions happens. For example, the most difficult area where the emissions can happen is the core. I mentioned that. If the core blasts for some reason, the rods which are there, which are controlling the heat generated, suppose they malfunction or the control system malfunctions, we take care of all of them. But suppose in spite of all this and an accident happens, the enclosure which is designed for any nuclear reactor is called containment. It is so strong that it keeps all the radiations within the system. Even after that, there will be some small radiations which will take place, which are governed by what is called the liability clauses. The people who have done that, they are being subjected to the liability clauses. So they are responsible. For example, when Fukushima accident took place in Japan, the people who suffered were provided for in terms of money and material by the insurance agencies, which are actually responsible for ensuring the safety of that plant. So they were compensated for. Similar provisions are there in our Atomic Energy Regulatory Board provisions also. Liability provisions are there.
Yes.
Okay, so the next one would be from Gayatri Ashok, Government Degree College for Women.
Actually, there is a very, very well written drill which is there in every plant, how to handle an accident. If you visit one of the plants, they will explain to you, right from the detection to ultimately controlling it, what all each individual has to do, what is to be done. Am I correct? That is the way it is handled.
The next, Gayatri Ashok. Yeah.
Sir, my question is about usage of nuclear power in space technology. Can nuclear energy be used in rockets as fuels in place of hydrogen as we use today? And how will it help us reduce the stages of the rocket or the bulkiness of the model?
See, I showed you some nuclear energy being used as a propulsive power for torpedo. Nuclear energy is used as a propulsive power for missiles. Nuclear energy is used as a propulsive power for submarine. So it can be used anywhere. If hydrogen is used as a fossil fuel, the same power can be generated by a nuclear power plant also, and it can give you the propulsive power or thermal power or electricity, whichever is the mode for which you want to use the energy for. So it can replace any action.
Sir, I have one more question. Nowadays, electronic vehicles are becoming very famous.
Pardon?
Electronic vehicles are becoming very famous nowadays.
Electrical vehicles.
Yes, sir. And can we make compact SMRs so small that could be fit to run those vehicles instead of using electric?
Very good question. Yeah, we should aim for that one day, that a simple SMR which I mentioned to you can be miniaturized so much that it can replace an automobile engine. But it still has not come to the footprint which I mentioned to you. Even today it's so large that it cannot happen. But yes, already there is a movement in terms of micro-nuclear reactors. Micro-nuclear reactors are moving practically in that direction to reduce the size, because what you need is not even 1 megawatt. What you need is kilowatts of power. So what you have to miniaturize and reduce that. So to create that 1 kilowatt of power, the paraphernalia is very large, and that's why the footprint becomes more. But I think the day will come when with new materials, with new control strategies, it would be possible. I'm not saying that it won't be possible. It will be possible.
Good. Thank you, sir.
So next question will be from Harini, Ambitus World School.
Good afternoon, sir. So my question is, so while we are producing nuclear energy, we know that radioactive waste is produced. So in the long run, is it really possible to store that radioactive energy, and won't it possess any danger?
Yeah, in fact, one thing that goes against the nuclear energy is the nuclear waste. I also mentioned in my talk. So there are ways and means of doing nuclear waste. One is reprocessing the nuclear waste. Our BRC, they are having technologies to reprocess and use it as a fuel later on. So that is one way. Second thing is store in such a manner that it does not contaminate the environment. Storage becomes very important. So the advantage of, I showed you in that, there is a recycling that takes place. U-239 is recycled into the reactor. U-230, the plutonium, all that is getting recycled. So what comes out as a waste is only a small quantity. So we can store them but storage also because they are radioactive at that time. Their half-life is very long. So we have to store them for many years, and then only they will be safe. So reprocessing is the answer. Cheap and viable reprocessing technology, R&D in that area is a very important part, and that has to be done. Am I correct, sir? All of you are experts.
Did that answer your question?
Yes, sir. Thank you.
Good. The next question will be from Asadullah.
Because I am answering your question.
Asadullah from Excel Ed School. Yeah, here is.
Sir, my question is, what will happen after some years or century? What will happen if the uranium will be extinct?
Uranium will be extinct. We will be finished. Uranium is reproduced. You saw all the reaction. We are getting fuel from fuel. Only thing is, waste is created. So some waste will go, then reprocess the waste. That's why we are talking of. If uranium is not there, then plutonium will be there. Plutonium is not there, thorium will be there. Thorium is available.
Yes, sir, thorium.
India has got 21% thorium of the world. So it will run for millions of years.
So we don't have to worry about it.
You don't have to worry about it.
Exactly. Good. Thank you, sir. We have got a question from one of the faculty. He is asking, sir, what type of liquid metals are used in SMRs?
I think, if I am not wrong, they are using, one is of course sodium, lithium, and one more is there, lead, if I am not wrong. These three are the main identified.
Okay. So
Sodium, of course, is the main.
definitely. So one more question asked, how use of nuclear energy will help in the climate change?
I think that lecture was all about that. The climate change is what? Climate change is happening due to global warming. Global warming is due to carbon emissions. And if you have to contain carbon emissions and you have to produce new energy for your growth, you have to use nuclear energy. That's all, simple answer.
Thank you, sir. One more question we got through online that it asks, if nuclear power is going to replace thermal power contribution, maybe more than 60%, what will be the position of the present mining and its infrastructure, including manpower? It's asking about mining, how much of mining is required?
Yes, I agree with you that every time when there is a shift, for example, today we are doing a lot of mining for coal, and if the coal is not going to be used for energy production, and nuclear energy is going to be there, then the coal mining will be reduced to a certain extent. But in my opinion, the coal mining can continue even when the nuclear energy is there. In fact, I would use nuclear energy for mining operations, so that even the carbon footprint of mining also comes down. So that is one. And coal can be used today with my method in a carbon-free mode. How it can be done? Coal should be gasified. Instead of burning coal, you should gasify coal. When you gasify coal, you produce carbon monoxide and hydrogen, which is called syngas. And that syngas can do wonderful jobs. It can make chemicals like methanol, it can make ammonia, it can make polycarbonates, or you can extract hydrogen from it and carbon dioxide from separately. Use carbon dioxide for whatever you can do with, make graphene, make aggregates, make many things. If surplus is there, put it in the geological storage. So as a result, even with coal, you can produce carbon-free power. This is called clean carbon technology. With coal, low carbon intensity, we can use. Hydrogen is produced, which is very, very clean. You can use automobiles running on that with the fuel cell. You can drive automobiles. You can use hydrogen as a energy storage, take it from one place, convert into methanol and ammonia, which are the carrier for hydrogen. In fact, today the problem what we are having of batteries not able to drive our large size vehicles, like commercial vehicles. You can't drive, because the weight of the battery itself runs into 3 to 4 tons, which is equivalent to the total payload capacity of that. So what you do, instead of that, you take methanol. Methanol you reform, convert into carbon dioxide and hydrogen with a reformer process, which is a very small fridge-like equipment. This hydrogen you use on a fuel cell, generate electricity and run your motor for running the propulsion system of the truck. This is the best method, low-hanging fruit today. Any industry wants to employ it, it is available. Reformer has been developed indigenously by 2 companies, and so we can do market that. And how do you generate methanol? From coal. So coal mining will get reduced, but there are alternate uses of coal which will keep the mining operations on. But certainly there will be certain level of unemployment because the intensity of mining will come down. That will have to be done on different processes, different areas. We have to find vocation for them in some other areas.
Thank you, sir. It was indeed very good. And one more, Dr. Vijay Manjanta would like to ask a question online, sir. He'll be asking you directly.
Yes,
sir, you can go ahead, Dr. Manjanta.
Can I see him?
Yes, here Dr. Saraswat.
You can see him.
Ha, sir. Namaskar.
Okay. See, my name is Manchanda Dr. Saraswat. I am ex-BRC. Are you able to hear me?
Yes, I can hear you and see you also.
Okay. So my question is very simple. Actually, you are a policy maker. So I refer to your last slide, SMR and private sector. So my question is that SMR you have already mentioned, that still they are not commercially viable. I mean, for various reasons. But still you are proposing SMR with, linking with private sector. But even if you remove SMR, my question is, this private sector will be always looking for commercial viability. And for historical reasons, various reasons, in India, the private sector has not entered the nuclear industry, unlike in the Western world. So what type of policy changes or how do we induce the private sector? Because you are a policy maker. So what do we do to induce private sector to also join the government in this area? So what are your views on that?
I think part of the, if you have listened to my talk, part of the answer was given there. There's a policy framework and there's a financial aspect and there's a market pull. These 3 factors are very important. Now, today, first thing that you have to do is modify the Atomic Energy Regulatory Act. There are clauses which prohibit today participation of private sector for various reasons. Clause number 3 or 4, we have gone into details with Dr. Vyas, I don't remember the numbers now. Those clauses have to be modified. That will be the first hurdle removed for private sector to come. Number 2, the power purchase agreements, like we have done in the case of solar power or hydel power we are doing nowadays. We have to also create a similar system for power purchase agreement. Number 3, we have to also get the similar incentives like PLI schemes or incentives like subsidies or viability gap funding for the private sector to get compensated for the kind of tariff difference which comes between a conventional solar power and the base load power from nuclear. If that will not be done, then you will have a problem. So we need to get some of these factors. And 4th thing is, we have to have a mixed system of private participation. For example, the regulatory body can still remain as part of the AARB's domain, so that the design, the manufacturing, the quality and the safety aspects as per the requirements are met. And the Department of Atomic Energy should act as a catalyst for hand-holding the private sector in terms of not falling into the lap of more and more foreign companies. Instead of that, they should fall into the lap of Department of Atomic Energy. That means you are the one who should give the technology to them, support them, make them do build, operate by your training, experience and technology transfer, rather than they going to Westinghouse and bringing one plant and blindly setting up in the country. That should not be our goal. Our goal is whatever comes, even if it is coming from outside, a SMR may come and tomorrow a new scale may come and give you a SMR from US. But I want transparency in that, in terms of design of new scale. Then my design, the design should be cleared by the authorities, AERB and others, and maximum number of industries in India should be exploited for manufacturing them. If you bring that kind of a policy framework with these inputs, I am quite certain the private sector will come into this sector. So far, we have not allowed them. We are using them only subcontractor for manufacturing components and devices, which is not enough. What we need is a complete power plant being set up by them, but under regulatory guidance of Government of India.
Thank you, Dr. Saraswat. Thank you.
Thank you, sir. So I think we will wind up the question answer session here, and I request our chief guest, Dr. Saraswat, to take the seat, sir, for a minute. And meanwhile, I request Director AMD to join him on stage.
Okay.
So you can take seat.
I have to sit here.
I request Mr. Avani to help Director AMD to felicitate. Yes.
Discussion was very good, sir. Thank you, Sankari AMD.
Thank you.
This is a memento what we have given, sir, for lecture series.
Thank you.
Sir, thank you, sir.
Thank you, sir. Thank you, Dr. Saab.
I don't know how long I spoke, but
Okay. Now I invite Dr. T.S. Sunil Kumar, Additional Director R&D, to propose a vote of thanks.
Good evening. And in fact, it was a scintillating event, and we have a very illustrious speaker with us, Dr. V.K. Saraswat, a former Secretary DRDO and presently the member NITI Aayog, who has very succinctly brought the concept about the nuclear technology and its future, and particularly his ideas and his vision about the small modular reactors. The highlight of today's lecture is he has presented his concepts, his knowledge with all of you, particularly the students, both from the university and the school level, high school level. And the interaction which has taken it to a totally new level, where he has brought many other things which he has not probably discussed during his presentation, which through the questions people have probed, sir, to give the answers which has brought to the knowledge. Actually, as Director AMD has mentioned, Indian Nuclear Society, in association with AMD, has organized this webinar series on the occasion of the Azadi ka Amrit Mahotsav. It started, the 10 lectures started with Dr. Anil Katkotkar, former chairman Atomic Energy Commission, on a topic on nuclear technology and its utilization, their energy security. Actually, he was emphasizing and bringing it. And we are closing this 10 lecture series with none other than Sir Saraswat sir, on a topic which is close to the entire DAE community and all the technology community in India who look forward for the development of the nation. So on this occasion, on behalf of entire AMD fraternity and Indian Nuclear Society, Hyderabad chapter, I take this opportunity to express our deep sense of gratitude and thank you for sparing the valuable time to be with us here and giving an excellent presentation. And this occasion, as usual, has been honored by the presence of our beloved Rear Admiral Sanjay Chaubey Sahab, who is the CMD ECIL, and Dr. N. Sai Baba, former CE NFC, and presently the Raja Raman of Law, along with my many senior officers who have joined here. My co-additional director is B. Saravanan is here. All the regional directors of AMD and heads of groups are available here. Many luminaries in the nuclear science and technology from NFC, BARC, and many other units have joined virtually this system, including former directors and additional directors of AMD. I express gratitude to all of them and all my colleagues who have joined here physically here. But last but not the least, the most important aspect is the student community and their faculties who have joined us both virtually and physically. We have, sir, the Osmani University students and faculty here. Some of them have, particularly from the Applied Geochemistry Department, who has come here physically. And Mathrusri Engineering College from Hyderabad. We were expecting them to be here, probably their academic curriculum, they have joined online. And Government Degree College for Women, they have also joined. Another 6 schools have joined, and the names have been already told, sir, and you have interacted with them. I thank all the students, both from the universities and the engineering college and the school children, and also their faculty for sparing time and interacting. I'm sure that a lecture would have helped you to understand many things about the nuclear science and technology and the future of the country as far as energy security is concerned. I thank all the INS members and the organizers who have helped us to organize this program in a very lucid, in a very successful manner. Thank you, one and all.
Thank you, sir. Now we will all stand up for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, one and all. And I request all of you to join us for a cup of tea along with our chief guest in the foyer. Thank you.